Hi everyone. We are continuing our review of Module 2. If you remember, we were discussing the Navier-Stokes equation and different limits of Navier-Stokes equation when a dimensionless ratio defined as Reynolds number would go to very small values, much smaller than 1, or very large values, much smaller than 1. We noticed that in these limits, we have certain asymptotic forms of Navier-Stokes equation, namely a Stokes equation at low Reynolds numbers and Euler equation at very high Reynolds numbers, for which we can find some tricks and some solutions in certain cases. However, there are some other cases that may have exact solutions. Some of these cases have a special nature, and in this module, in Module 2, we actually dealt with some of them. They were categorized under the name of problems which have similarity solutions. Similarity solutions are applied to problems where you can find a similarity parameter. What really means, what we do really mean by a similarity parameter is a combination of one or two important scales in the problem in a manner that it makes the whole thing collapse on a universal behavior or a universal curve. In simple words, this is usually applied to problems where there is no physical scale that length scale, for example, or time scale that you can easily detect by the nature of the problem. If you remember the Rayleigh problem, or some people call it the Stokes first problem, where you have an infinitely long plane that is sitting at y equal to 0, and the x-axis is just parallel to the plate. We had this issue that we wanted to solve this problem when there was no motion. It was relatively simple. When the ball is not moving, everything on top, which is a fluid with density rho and viscosity mu, probably sits on the plate happily with just hydrostatic balance. So if you like to think about density and viscosity of this liquid rho and mu, is given to us. But we ask ourselves what will happen when we impulse this plate from zero velocity to a finite velocity that is given to us, u, and we keep moving this plate from left to right with velocity u. In this case, we have a special case of Navier-Stokes equation, which is transient in nature, and so we cannot ignore all the inertial terms. There's a certain acceleration term that comes due to the transient nature of this phenomena, and we need to keep that. But we don't really know anything other than that before we really think about some assumptions in this problem. We very soon notice that due to the fact that things are not changing from minus infinity to positive infinity, the plate is exactly the same geometry all through the domain that we have in terms of x axis. And the pressure is not having any gradient. Pressure everywhere is constant. We concluded that we can easily see that say that d over dx is 0. Things are not really changing with respect to x-axis in this problem. Once we use that information, if you remember, we combine that with the fact that flow is incompressible. So the divergence of velocity is 0, and that simply tells us that dvy over dy should be also 0. Because dvx over dx is automatically 0, and their sum, which is the divergence of velocity, is 0. So we conclude that dvy over dy should be also 0, which tells us vy should not have any variation with respect to y. And we know that vy at the wall is 0 because this wall is a rigid boundary and there is no flux through it. So that simply tells us that vy everywhere is 0. And vy everywhere being 0 and things not varying with x tells us that the solution that we are looking for should be only having one component in terms of velocity. That's only the x component of the velocity that remains non-zero, vx. And it can only be a function of y and time in this case because the problem is transient. It cannot be a function of x because d over dx is 0, and vy is 0 just because of the simple trick that we use this assumption and implement it inside the continuity equation. That brought us to this simplified version of Navier-Stokes equation. So from left-hand side, the only term that is remaining is the transient term dvx over dt. The right-hand side has mu usually, which is dynamic viscosity. We divide that over rho, and that gives us this new concept or new parameter, nu, called kinematic viscosity, which is mu over rho, and has dimensions of meter squared over second. So we need to really solve this equation. And if you remember from your notes, like any other equation, this is a partial differential equation. It has two derivatives with respect to a space and one derivative with respect to time. So we need one initial condition and two boundary conditions. The initial condition is at time 0, nothing is happening. The whole phenomena is stationary. So velocity as a function of y at time 0 everywhere in a space is equal to 0. So that's our initial condition. However, we know that once we start moving the plate, there is a certain boundary condition which is happening right at the plate. Due to no slip boundary condition, what we will have is Vx at y equal to 0 and times larger than 0 should be non-zero and finite, and that's the given wall velocity, which is u. Similarly, if this is the no-slip boundary condition that is happening at the wall, we can also say something about velocity of fluid elements which are extremely, in fact infinitely, away from the wall. Imagine a point that has a huge or a very large distance from the wall. That specific point will not really feel the fact that we have started moving the wall. Because when we start moving the wall, if you look at the movies that we have shown in the lectures, fluid elements gradually notice the motion of the wall due to the friction between different layers of fluids. And it takes certain time for that information to really reach fluid elements above. And we characterize that based on this increasing zone of friction or zone of viscous effect, which we call delta of t. And we said that this delta of t is growing with time. Initially it's 0. As we start moving the plate, it's going to grow to larger and larger values. But it never really reaches infinity. So infinitely far away from the wall, we have the fact that fluid elements will not feel this motion. They still feel that the wall is stationary. So if y is infinity, for times larger than 0, their velocity remains indeed as it was before, which is 0. So there you go. We have a certain partial differential equation. First order in time, one initial condition. Second order in the space, two boundary conditions. One for the wall and one infinitely far away from the wall. What we clearly see, this problem is unbounded in the y dimension. There is no length scale in the y direction. In fact, the only length scale that we have, which is delta of t, which captures how viscous effects are slowly and gradually diffusing inside the domain or entering our domain, is a length scale that is actually evolving with time. So delta is moving or increasing with time and is a function of time. So something tells us that probably this is a good problem to apply the similarity parameter and similarity transformation, because we don't really have a clear length scale that was given to us. If there was another wall with a finite distance h on top of this lower wall, then we had a given length scale. And for that problem, probably similarity solution would not be the appropriate approach. But here, since we don't have really any length scale on top, we need to use this information that delta is indeed evolving with time and define our similarity parameter based on that. And in fact, if you look at your notes, what you will notice is we continued by saying that if Vx, the x component of the velocity, is in this problem a function of given wall velocity u, and it can also vary with y. It can also vary with time, as we discussed here, y and time. And it's also probably depending on the important parameter that enters our equations, which is the kinematic viscosity. And sometimes people say that, oh, it may depend on both rho and mu. That would have been correct if we had some other terms here. But since the only term left is this one, which had mu and rho here, and we take the ratio of them, the governing equation tells us here that the only important parameter from the fluid that enters our governing equation is the kinematic viscosity. In other words, if I find the solution for something like water, but if I find another liquid that has a viscosity 2 times water and density 2 times water, so that the ratio of them would give me the same kinematic viscosity as water, the solution for water applies for this new liquid absolutely correctly in a similar manner. It's only the kinematic viscosity that enters our governing equation. That's why we only have that parameter. And here is the point that we can use a little bit of our knowledge about dimensional analysis. And I think this is a good point to pause, and we continue that in the next video. But just to remind ourselves, the way we set up the problem is the velocity goes inside this partial differential equation. It has certain initial and condition and two boundary conditions. And we are trying to use dimensional analysis to see how we can actually explore this and find something slightly more useful in our search for the final similarity solution. We continue that in the next video.